So 3.1 has quite a few topics in it, and they're mostly centered on dilations. So we need to talk about two definitions to begin with. The first is congruent, and the next is similar. And these words apply to polygons, but they also apply to other 2- and 3-dimensional shapes. So it could be we're talking about rectangles, it could be we're talking about stop signs. We could also be talking about 3-dimensional shapes like rectangular prisms or cylinders or any of those. What does it mean to be congruent? What does congruent mean in geometry? Same. It's a little stronger than same. Same measures. Yeah, so congruent pretty much means exactly the same in every way, except maybe orientation. So all of the sides and angles are the same between two shapes. So if I drew a square, a congruent square would have to be exactly the same size. What if I rotated it? Is it still congruent? Yes, it is. So orientation doesn't matter, but as far as angles and sides go, it's exactly the same. All right, what does similar mean? We can use the word same again. So similar means same shape, but it could be a different size. So if I had a hexagon, and then I had a smaller hexagon, but it's still regular, all of the angles match. But is it just angles? Could I draw a hexagon that has the same angles that's not similar? That has the same angles. Would you consider that similar? No. So something else has to go on. The angles all have to match. But what else has to be true to be similar? Side lengths have to be the same ratio, or we could use the word proportional, right? So let's say I had a small rectangle, and the lengths on the rectangle were 3 and 7. Okay? We can do a bunch of transformations to that. If we slide a rectangle around, do you guys know what type of translation that is? Oh, it's just a translation. I meant, do you know what type of transformation it is? I gave away the answer. So the transformation that is done by sliding that rectangle around is called a translation. What if I flip it? What's that called? Right? What if I draw a line, then I flip it over, and I get this? That's called a reflection, all right? What if I grab it and I spin it? That's called a rotation. So we have translation, moves things around. Reflection does the mirror image. Rotation spins. And then how would we change its size? What's that called? That's called a dilation. Okay. Now, on a computer, when I pick this rectangle, maybe. Why is that not working? I don't know. That's really weird. My computer's having a hard day. Won't let me choose that. Huh. Not sure why. So if I were to click on this, I would get sort of a box here. And I would have the choice to pull on the corners, or I could also pull on the sides. If I pull on this side, is that considered a dilation? No. A dilation has to preserve similarity. So I can only pull on the corners. And it has to remain similar. So let's say I dilate this, and I end up with this rectangle. All dilations preserve similarity. Okay? So let's say that this new side here is a 12. What would this side be? Why 28? So we are going to find the ratio of dilation. So if I go from a big, or that's not what I did, from a small figure to a big figure, my ratio of dilation is going to be bigger than 1. My ratio will be greater than 1. Okay? And in this case, the ratio is really easy because this side is proportional to that side. So 12 divided by 3 is 4. That is the ratio of dilation. So everything in this shape is going to be 4 times bigger, right? Well, let's look at it. So 7 times 4 is 28. Okay. What about the area? Is the area 4 times bigger? Well, what's the area of the small one? 21. Oh, good. So the area of this is 336. So what happened between 21 and 336? Well, if I take 336 and divide it by 21, I get 16. Why did I get 16 for the area? Oh, so the ratio of dilation, also called the scale factor, is 4 for the bottom and 4 for the side. So this is a two-dimensional shape. The left-right got 4 times bigger. The up-down got 4 times bigger, which means the area is 16 times bigger. Okay? What would happen if I had a cube and I doubled its size? What would happen to its volume? So it would be 2 times bigger in the x direction, 2 times bigger in the y direction, and 2 times bigger in the z direction. So doubling the size of the cube is going to make the volume 8 times larger. Okay. Well, what if I did the dilation in the other direction? So what if I dilated from this to that? What would the scale factor be? So the scale factor is always the future shape divided by the past shape. So in this direction, the scale factor is 4, but in this direction, the scale factor is 1/4. Now, there are a whole bunch of different types of questions on ALEKS. Some of them have sliders, so you move the slider until it reaches the right number to figure out what the scale factor is. It will give you the scale factor and ask you to figure out where did these points land. If I had a shape in space, so I had this shape here, and it told me this is 1, 2, and this is 3, 1, and then this is 1, -3. Okay. If it says that the scale factor is 2, can you figure out where those points need to go? So how would you do that? Well, we would just go in and double every single point. So 1 comma 2 would now be 2 comma 4. 3 comma 1 would now be 6 comma 2. 1 comma negative 3 is now 2 comma negative 6. And my new shape is twice as big as my old shape, as far as the side lengths are concerned. Right, that's it. Get to work.